For over a century, human engineering has been defined by friction. Building complex machines meant relying on dense, manual assembly lines, where every single component had to be perfectly aligned and secured by human hands. Even today, our most ambitious projects are held back by three stubborn bottlenecks: the logistical strain of assembling thousands of intricate parts, the energy required to maintain extreme lab pressures, and a reliance on limited human observation. Across just 7 days in the third week of May 2026, research teams in 3 separate fields bypassed these physical and logistical limitations simultaneously. These breakthroughs in aerospace, physics, and ecology provide a practical framework for a future where progress is no longer tethered to manual assembly or biological reaction times. On May 19th, the Indian space tech startup Agnikul Cosmos completed a simultaneous cluster test fire of 4 semi-cryogenic rocket engines. Typically, building a multi-engine configuration is a logistical nightmare. It involves sourcing, machining, and painstakingly piecing together thousands of individual, intricate parts. This test was different. Each of the 4 engines was built entirely in-house, 3D printed as a single, solid piece of hardware. Printing complex components as single items eliminates the need for massive assembly lines. Production timelines shrink from months of manual labor to mere days of automated printing. In this model, the pace of rocket production is no longer capped by how fast humans can bolt metal together, but only by the speed of the printers. Superconductors carry electricity with zero resistance, but this state traditionally required extreme pressure, like the forces at a planet's center. Yet in mid-May, researchers successfully induced superconductivity in a copper-based compound at standard atmospheric pressure. Instead of maintaining constant compression, the team achieved the phase change through a sudden, highly controlled release of pressure. Removing the need for hyper-pressure containment makes zero-energy loss power grids and more efficient computing physically viable for deployment outside of a laboratory. The San Francisco Bay is a vast, high-traffic waterway. Traditionally, preventing cargo ships from striking migrating gray whales relied on human spotters, who cannot monitor these massive shipping lanes fast enough to prevent collisions. To solve this, an active AI-driven marine conservation ecosystem was deployed this week. This map shows how the system removes the human observation bottleneck. Automated networks scan the water continuously, mapping whales in real time. Once detected, the AI beams telemetry directly to vessels, allowing them to dynamically alter course or slow down. This shift allows heavy maritime industry to coexist with migrating ecology by removing the reliance on manual human reaction times. Over the last 7 days, we have seen 3 distinct disciplines bypass the constraints of slow assembly, extreme lab environments, and biological processing speeds. Based on the Agnikul Cosmos test, aerospace is moving toward a model where complex multi-engine rockets are manufactured in days rather than months. The superconductivity breakthrough provides a path for power grids and data centers to operate without specialized high-pressure containment systems. In the shipping industry, trade routes can now dynamically adapt to the movement of nature in real time. These developments from May 2026 establish a new baseline for speed and efficiency. They provide the practical blueprint for a world where manufacturing, energy, and ecology operate without the traditional friction of human logistics.